In question 1, we are applying Hamming error correction code to identify and fix single-bit errors in binary data. Our objective is to compute new check bits from each given 10-bit data word, compare them with the original check bits, which are 0011, and use the result to determine if there's an error and where. Once the error is located, we flip the incorrect bit to recover the original correct code word. Let's start with data word A. 10011100001. We place the bits into a 14-bit Hamming format with parity bits at positions 1, 2, 4, and 8. We then calculate each check bit using XOR logic on the respective position. P1 becomes 1, P2 is 0, P3 is 0, and P4 is 0. So the new check bits are 1000. Next, we compare the new check bits 1000 with the original 0011. Using XOR, we get a syndrome of 1011, which equals 11 in decimal. This tells us that the error is at position 11. The original bit at position 11 was 0, so we flip it to 1. The corrected code word is now 10011. Now for part B, the second data word is 00011011101. Again, we arrange the bits in the Hamming format and calculate the new check bits. P1 becomes 1, P2 is 0, P3 is 1, P4 is 0. So the new check bits are 1010. We then XOR the new check bits 1010 with the original 0011. This gives us a syndrome of 1001 or 9 in decimal. That means there's an error at position 9. The bit at position 9 was 1. We flip it to 0, so the corrected code word becomes 000110101. To reflect on these questions, Hamming code is a simple yet powerful method for detecting and correcting single-bit errors. Understanding the correct positioning of data and parity bits is critical. The most challenging part was interpreting the syndrome and mapping it correctly, especially when working with an expanded. For question 2, we're working with Booth's multiplication algorithm, which is used to multiply signed binary numbers using 2's complement representation. The objective is to multiply x equals to -12, y equals to 4 using a 5-bit word, and x equals to 15, y equals to -8 using a 6-bit word. Here's a quick overview of Booth's algorithm. First, convert both numbers to 2's complement binary format. Second, initialize 4 components. A equals to 0, Q is multiplier, M is multiplicand, Q minus 1 is 0. Then, for each bit in the word size, if Q0, Q minus 1 is 10, subtract M from A. If Q0, Q minus 1 is 01, add M to A. Otherwise, do nothing. After that, perform an arithmetic right shift on AQ and Q minus 1. Once all steps are complete, we combine A and Q for the final results. In part A, we multiply -12 and 4 using 5-bit representation. So x equals to -12 becomes 10100. Y equals 4 becomes 00100. We initialize A equals to 00000, Q equals to 00100, Q minus 1 equals to 0, and M equals to 10100. The process goes through 5 steps. Step 1 and 2, Q0, Q minus 0 equals to 00, so we only shift. Step 3, Q0, Q minus 1 equals to 10, so A equals to A minus M. The result is 01100. Step 4, Q0, Q minus 1 equals to 01, so A equals to A plus M. The result resets to 00000. Step 5, shift again with no operation. The final results from A plus Q is 000001100, which is 56 in decimal. So, -12 times 4 equals to 56. Now, in part B, we multiply 15 and -8 using 6-bit format. X equals to 15 is 001111. Y equals to -8 is 111000. We initialize A 00000, Q 111000, Q minus 1 equals to 0, and M 001111. The algorithm goes through 6 steps. Step 1 to 3, Q0, Q minus 1 equals to 0, 0. So we only shift. Step 4, Q0, Q minus 1 equals to 1, 0. So A equals to A minus M. Results is 1, 1, 0, 0, 0, 1. Step 5 and 6, Q0, Q minus 1 equals to 1, 1. So no operations, only shift. The final combined A and Q is 1, 1, 1, 0, 0, 0, 1, 1, 0, 0, 0, 1. Since it starts with 1, it's negative. Taking its 2's complement gives us 207, so the final result is negative 207. Boost algorithms is a powerful way to multiply signed binary numbers. It was interesting to see how it reduced unnecessary operations by recognizing bit patterns, especially when handling sequence of ones. The key challenges were handling 2's complement math and applying the arithmetic right shift correctly at each step. Overall, it gives a solid understanding of how multiplication is implemented in hardware using logic circuits like the arithmetic logic unit or ALU. In question 3, we are applying the restoring division algorithm to perform binary division using 4-bit integer representation. We are asked to compute two operations, which is 7 divided by 4 and then negative 5 divided by 2. The objective is to determine both the quotient and the remainder following the step-by-step binary division method. Here's a quick overview of how the restoring division algorithm works. So we start with A equals to 0 as the accumulator. Q holds the dividends and M holds the divisor. A temporary bit Q minus 1 is used for shifting. Each step includes first, shift left the A and Q registers. Second, subtract M from A, which becomes A minus M. If A becomes negative, we restore it by adding M back and set Q0 equals to 0. If A stays positive, we retain it and set Q0 equals to 1. At the end, the quotient is in Q, the remainder is in A, and the sign of the final result depends on the original signs of the dividend and divisor. Now for part A, we divide 7 by 4 using 4-bit binary values. 7 is 0, 1, 1, 1, 0, 1, 1, 1, and 4 is 0, 1, 0, 0. The initial setup, A equals to 0, 0, 0, 0, Q equals to 0, 1, 1, 1, M equals to 0, 1, 0, 0. So we go through 4 cycles. In step 1, after shift and subtraction, A becomes negative. We restore A and set Q0 equals to 0. Same happens in step 2 and 3. In step 4, the result of A minus M is positive, so we set Q0 equals to 1. So the final result, quotient Q equals to 0, 0, 0, 1, so the decimal is 1. The remainder is A equals to 0, 0, 0, 1. The decimal is 1. Since both inputs were positive, the result is also positive. Now let's look at part B, dividing negative 5 by 2. So negative 5 is 1, 0, 1, 1 in 2's complement and 2 is 0, 0, 1, 0. So the initial setup, A equals to 0, 0, 0, 0, Q equals to 1, 0, 1, 1, M equals to 0, 0, 1, 0. In this case, step 1, A becomes negative after subtraction, so restore A. Q0 equals to 0. Step 2, result is positive, so Q0 equals to 1. Step 3, subtraction causes A to be negative again, so restore and Q0 equals to 0. Step 4, result is positive, so Q0 equals to 1. Now for the sign correction, dividend is negative, divisor is positive, quotient is negative, remainder stays positive or 0. So the final answer, Q equals to 0, 0, 0, 1, convert to 2's complement, so it's equals to 1, 1, 1, 1. So it's same equals to negative 1. So A equals to 0, 0, 0, 0, and the remainder is 0. These questions showed how sign division is handled in binary systems. A key takeaway is that the sign of the result isn't just based on the subtraction step, but depends on the original signs of the numbers. Another important part is to carefully track the accumulator and know when to restore A after a negative result. It's fascinating to see how computers might make long division through basic operations. In question 4, we explore how a one-address machine uses the accumulator, which is ACK, with different addressing modes. The objective is to analyze whole load instructions and determine the final value stored in the accumulator after each execution. Let's begin by understanding the 3 addressing modes used. First one is immediate mode. It loads the value directly into the egg. Next, direct mode. It fetches the data stored at the specified memory address. Next is indirect mode. It fetches the address stored at a given location, then retrieves the data from that address. We will apply each of these to a given memory table. Here's the given memory table. 10 equals to 50, 20 equals to 50, 30 equals to 40, 40 equals to 60, 50 equals to 80. We will now go through each instruction and evaluate the final egg value. First instruction, load immediate 40. Since it's immediate mode, we load the value 40 directly into the egg. So the result, egg equals to 40. Second instruction, load direct 20. This loads the data at memory address 20, which is 50. So the result, egg equals to 50. Third instruction, load indirect 30. First, we check M30 equals to 40. Then we get M40 equals to 60. So egg is loaded with 60. So the result, egg equals to 60. The fourth instruction, load indirect 10. So M10 equals to 50 and M50 equals to 80. So the egg loads 80. Results, egg equals to 80. This question was helpful in strengthening our understanding of how computer access memory using different addressing modes. It was clear that immediate mode gives the value directly, direct mode retrieves data from a memory address, and indirect mode requires an extra level of referencing. This logic is essential when learning about assembly language and how CPUs process instruction at low level.